the specific solution of the Einstein equations in vacuum. So this is a picture where you have at R equal R plus, you have the horizon, so-called horizon. The red line that you see below, which again, unfortunately, I cannot point. Is there a way to get a better pointer? It doesn't seem to work at all. Anyway, so the red line represents a space-like hypersurface on I'm sorry? It works better on this side? Is that true? No, I don't see anything. Does anybody see the pointer? Sorry? It's too light. Okay. You cannot see anything. Okay, that's too bad because I was hoping to be able to point out. Anyway, there is a red line. Think of the red line as being a space-like hypersurface in this Lorentzian manifold, which is represented in a compactified form. You have the boundaries, the so-called null boundaries, which are represented by scribe plus, scribe minus being the past boundary. These are all null hypersurfaces, and the red space-like hypersurface, think a bit of the place where you set up your initial conditions. So the Kerr solution induces, on this red line, induces the first and second fundamental form, which represents the initial data of the Kerr solution. Now you perturb it a little bit, think of perturbing the initial data a little bit, in such a way that you still satisfy the so-called constraint equations. So the constraint equations are necessarily, have to be necessarily satisfied in order to actually be able to solve the equation starting with those initial conditions. And anyway, so the statement of the theorem is very simple. The statement of the conjecture, first of all, is very simple. For any small perturbation of the initial data set of a Kerr solution, so Kerr solution is represented by two parameters, A and M, A being the angular rotation and M being the mass. The conjecture is that for any perturbation, you need the conditions on A over M has to be strictly less than 1. I think it's written there. Absolute value of A has to be less than M. Otherwise, you get all sorts of unfortunate features of the Kerr solution if A is large, if A is much larger than M. So the conjecture is for absolute value of A less than M, and the result that we have proved together with Jeremy Seftel in 2021, and also together with Elena Georgi, and Seftel and myself, in 2022. There is also an additional paper by Shen in 2022. Together, there are 5 papers which prove the stability of the Kerr solution for small angular momentum. Right? So let's go on. A little bit about the Kerr family. So these are solutions of the Einstein vacuum equation. So think of a Lorentz metric. Take this Riemann curvature tensor, from which you form the Ricci tensor by taking a trace. And the equation is just Ricci of G is equal to 0. This is called the Einstein equations in vacuum. Of course, there are more general equations, Einstein field equations, where you combine gravity together with various matter fields. But I will obviously, the conjecture, the Kerr conjecture, refers only to vacuum solutions. In other words, Ricci of G is equal to 0. It's a purely geometric equation. There are specific solutions that you can immediately verify. So, for example, Minkowski space, the Minkowski space of special relativity, is the simplest possible solution. There is a Schwarzschild solution discovered in 1916, actually, so a year after Einstein set up his Einstein vacuum equations. So this is a case when A is equal to 0 and M is different from 0. The full family of Kerr solution was discovered by Kerr in 1963. This is one of the major results in not just in general relativity, but in all of physics. It's one of the most interesting solutions in all of physics. And partly because it really corresponds to an extremely important physical object, astrophysical object, which are black holes. So the black holes are really described by the Kerr solutions. There is a slightly more general class of solutions called Kerr-Newman, where this do not correspond to the vacuum equations, and they are not considered nearly as important as the Kerr solutions. So the Kerr solutions really are at the heart of our understanding of the universe, and a little bit about general covariance. So it's going to play a very important role in what I'm going to say later, is that a solution of the Einstein equation, so ratio of G is equal to 0, is dependent on diffeomorphism. So, for example, the metric G and the pullback by the metric G by diffeomorphism M, diffeomorphism from M to M, phi, any diffeomorphism, these two things have to be considered from a physical point of view as being equivalent. So it doesn't matter which coordinate system you choose, the solution of the Einstein equation is exactly the same from a physical point of view. And this covariance, as we shall see, will play a fundamental role. So here is a Kerr family expressed in a particular system of coordinates, which is called the Boyer-Linquist coordinates. It doesn't quite matter exactly what it is. I'm not going to insist on the specific form. It's just to point out that it's really amazingly simple, given that it's a solution of one of the most complicated equations that we have in all of mathematics and physics, which are these Einstein vacuum equations. They are highly nonlinear, quasi-linear, hyperbolic, and so on and so forth. And here you have explicit solutions, depends only on these coordinates t, r, theta, and phi, which the r, theta, and phi are really polar coordinates. You can think of it in comparison with polar coordinates in Minkowski space. And you see that the coefficients of the metric are quite simple, expressed just in terms of algebraic and trigonometric expressions. So it's pretty impressive that such a thing is a solution of the Einstein equation. And even more impressive is that these are the solutions which correspond to astrophysical objects which are called black holes. All right, so here are some simple properties. The solutions are stationary and axisymmetric, which you can read immediately from the form of the solution by observing that all the coefficients do not depend on t and do not depend on phi. So it means that dt on d phi are Killing vector fields, we say. There is another symmetry, which is a hidden symmetry discovered by Carter. So this is a second order symmetry, leads to a second order operator rather than first order operators as dt and d phi. And plays a very important role in our proof. Okay, so this is the Carter operator. Another thing that you recognize is that these are asymptotically flat manifolds. In other words, if R, which is this parameter, is large enough, the solution gets closer and closer to Minkowski space. So for R going to infinity, you just get the Minkowski space, expressed in polar coordinates. So here is some other features of the Kerr solution. So there, excuse me, there are, unfortunately, again, I cannot point out. So there is a pair of vector fields which you see below in the picture below, E3 and E4. They are null vector fields, and they are normalized such that the scalar product relative to the Kerr metric is between E3 and E4 is equal to -2, so it's normalized. And you define then, so these are, by the way, I should say E3 and E4 are specific choices of null vector fields. It's called a principal null pair in Kerr solution. I'm not going to write them explicitly here. I just want to point out that there exist such things which have a lot of very interesting properties. You define what we call here chi bar. On the left, chi bar is a two tensor on EA, EB. So the EA and EB are vector fields orthogonal to E3 and E4. So they are part of what is called the horizontal structure. Horizontal structure is H is perpendicular to E3 and E4. You find the second fundamental form, chi bar and chi, by exactly as you do in geometry when you calculate second fundamental forms. Okay, so there are two second fundamental forms corresponding to the two null vector fields. So then you define the trace relative to EA and EB, so relative to the horizontal structure, trace of chi bar and trace of chi. But what's interesting is that there is also an asymmetric trace. In other words, chi and chi bar typically, when you define second fundamental forms, they are symmetric. Here they are not symmetric, which corresponds to the fact that the horizontal structure is not integrable. So the horizontal structure is not integrable. In other words, it's not tangent to hypersurfaces in Kerr. This is expressed in the fact that this A trace chi and A trace chi bar, so in other words, the alternate trace and alternate trace chi bar, are different from zero. So they being zero corresponds exactly, by Frobenius theorem, corresponds exactly to the integrable case. So this is not integrable. So the lack of integrability of this structure in Kerr also plays a fundamental role in our work. It leads to all sorts of very interesting difficulties which one has to solve. So it's very different from, say, the kind of structure used in the stability of Minkowski space, which was an integrable structure. This is not integrable, and you'll see it in a moment why it's important that it's not integrable. So here is a general framework now. Using somehow the Kerr solution, the properties of the Kerr solution, you can define sort of a general framework which will be useful for studying stability of the Kerr, so the actual stability of the Kerr solution. So in other words, you pick up a frame, so it's E3, 4. This is called a null pair. You take the horizontal structure, which is at every point the tangent space to E3 and E4. I mean, the space perpendicular to E3, E4. You define connection coefficients like chi and chi bar, which I had just mentioned. But you define many other coefficients. For those of you who know the stability of Minkowski space, you'll recognize that the notations are very similar. So you define so-called chi chi bar, eta bar, zeta, psi psi bar, omega omega bar. And as you see, chi and chi bar can be decomposed into the traceless part, which is called chi hat of AB, and the trace and the alternate trace. And again, A trace and A trace chi bar. So these alternate traces are zero if and only if you have integrability of the horizontal structure. And you define also curvature components relative to this horizontal structure, which are this alpha AAB, alpha bar AB. And there are, in addition, there are components which we call beta, beta bar, rho, and rho star. So again, for those of you who know the stability of Minkowski space, you recognize that these notations are very similar to the one that, in fact, they're the same. It's just that now you are in a non-integrable structure, but the definitions are exactly the same. So the next thing that you do is to complexify these Ricci and curvature coefficients. So for example, you can define, again, fortunately I cannot see, so in 5, you define capital X as being chi plus I, and the dual, Hodge dual of chi. So it gives you a complex tensor, the same thing with X bar, and also with what we call capital A, which is formed as a complex sum between alpha and alpha bar. So alpha plus I, alpha plus I dual of alpha. So alpha plus I Hodge dual of alpha. So again, Hodge duality is something that it's easily defined relative. So you call the connection coefficients. So the connection coefficients are this x bar, xi bar, h bar, z, and so on. So all these Ricci coefficients complexified. The curvature, again, after complexification, we have the capital A, B, P. P is actually rho plus rho I rho star. Rho is a scalar. Rho star is a scalar, so you put them together. That's something quite typical to these complexifications. In any case, once you set up all these things, you find, first of all, it's important to note that in Kerr, if you are exactly in Kerr for the principal null pair that I mentioned earlier, that is such that many quantities are exactly equal to 0. So in particular, x hat, x bar hat, xi bar, a bar, b, and b bar, they all vanish, right? That's extremely important because in perturbations, these are going to be small quantities, right? And obviously, you want to do some kind of analysis based on the smallness of various quantities. Okay, then the next thing that you do once you have all these quantities is you write down the Carter-Bianchi equations. So these are standard equations in geometry. So they look formally like d gamma plus some kind of nonlinear expression in gamma, comma, gamma is equal to curvature. So on the right-hand side, you have a curvature component. And the Bianchi identities are dr plus products between r and gamma equal to 0. Finally, after you have set up all these things, there is a major issue in perturbations of Kerr, which is what frame do you choose? I mean, after all, if you have a frame which verifies these properties, the important properties that you should look at are the ones of the vanishing of x hat, x bar hat, and so on and so forth. So the question, which gauge are you choosing? In other words, which choice of E3 and E4? And the natural thing to do is to see how, by making a null frame transformation, how all these quantities change, right? And this kind of null frame transformation will play a very important role. So in other words, you go from E3, E4, and the horizontal structure perpendicular to E3, E4 to another E3 prime, E4 prime, which are also null pair. So and H prime, which is again perpendicular to E3, E4 and E4 prime. And when you do that, and you have to look at all possible frame transformations, there are lots of them. Whenever you do them, the gammas change into gamma prime, and the curvature R, in other words, this curvature component, change into R prime. And you can easily see that you have a large class of null form transformations, such that the fact that x hat, x bar hat, and so on and so forth, the ones which are vanishing in Kerr, which are now O of epsilon, so epsilon being the size of the perturbation, when you make this transformation, you get the same thing. So in other words, you have a huge number of possible gauge transformations, which have more or less the same properties. So the big question in the subject is what gauge are you using in order to prove convergence? In other words, in order to prove the stability result. All right, so okay, so what are the main difficulties? There is gauge fixing, right? So you have to, if you remember, the stability result tells you that if you perturb a Kerr solution with parameters A and M, you converge to a Kerr solution, but not the same. You may converge to one which has different final parameters. It has A final and M final. So the final parameters you don't know a priori, and you cannot measure in terms of the initial data, right? So initial data, you have a given Kerr solution with parameters A and M, but you cannot determine a priori, you cannot determine what A, F, the final A, and the final M are. So this is one major difficulty. The other major difficulty is that conversion to the final state is gauge dependent. So in other words, unless I find a gauge in which I know how to control decay and I know how to show that all the quantities decay at correct quantities in the final state, I'm stuck, right? And of course, decay, so it's an issue of decay, right? In other words, time decay. So of course, we all know the solutions of the wave equations decay. There is a dispersion, but the dispersion, the way you express the dispersion clearly is coordinate dependent. So this is more or less what's happening here. These things are gauge dependent. So the convergence to the final state is gauge dependent. And finally, the final parameters, in other words, the final A&M, and the final gauge will only emerge in the limit. In other words, again, you cannot determine them from initial data. You just have to construct them from infinity somehow. All right, so that's the issue of quantitative decay already mentioned. First of all, it's very different. The proof is very different from the one in the stability of Minkowski space, in that in the stability of Minkowski space, all curvature components are supposed to converge to zero, right? Which is Minkowski space. In Minkowski space, all curvatures are zero. Here, that's not true. There are components of the curvature which really will be non-zero in the limit, and you have to somehow separate the two. And the separation is actually one of the most complicated parts of the whole thing. It turns out there are some equations which are called Teokolsky equations, which are equations verified only for certain components of the curvature, which are called the extreme components, A and A bar. They verify so-called Teokolsky equations. You have to analyze the Teokolsky equation. This is nonlinear hyperbolic equations, whole theory of hyperbolic equations, which I'm not going to get into it. But the other thing that I should say is that it's not the Teokolsky equation. Teokolsky equation by itself doesn't have good properties. You have to really do a transformation, which is a highly non-trivial transformation called the Chandrasekhar transformation, which leads you to a different equation, which is called the generalized Regge-Wheeler. So what I have there is GRW. So these are equations for A and A double bar. And a large part of the proof of stability of Kerr is to deal with these quantities. Okay? But again, this is not, and the important thing is that these quantities A and A bar are in some sense, they are gauge invariant, at least relative up to quadratic nonlinear terms. They are gauge invariant, and therefore they are not so sensitive to the change of coordinates. Right? So there are some kind of universal quantities which do not depend too much on the coordinates. So that's very important. And of course, another thing that you have to keep into account is that decay, in other words, time decay, should always be measured relative to the decay of wave equations in Minkowski space. And you have a dispersion, which is important. You have energy estimates, or energy identities rather, for the wave equation in Minkowski space. The decay or pointwise decay is a consequence of dispersion of waves in Minkowski space. So you have to have some similar mechanism in nonlinear perturbations. This is a very complicated story, which I'm not going to get into it because I want to emphasize more the quantities. How do you treat the quantities which are gauge dependent, right? So the only quantities which are not gauge dependent, at least up to quadratic terms, are this A and A bar, the Minkowski bar. All the other ones are heavily gauge dependent. And the issue is how to treat them. So, okay, so this is a stability result with a little more details. So you have initial data, which is represented by sigma 0, the low side of the diagram. And you still have initial conditions, which are perturbations of the initial conditions of Kerr, and you construct a space-time which has a complete future null infinity. So complete future null infinity simply means that at infinity, if you are far away, the infinity is represented by this compactified picture is represented by this I plus. I plus is complete. It means an observer which is very, very far away from the black hole. The black hole will have to be close to the old black hole that you perturb. So if you are far away from this, you can live forever, right? In other words, what is called complete future non-infinity is just a way of saying that an observer which moves far away from the black hole can live for a very, very long time, okay, before it hits the black hole. So anyway, so this is sort of a global feature of the Kerr solution. You have a convergence to this new Kerr solution, which has parameter infinity and infinity, which, as I said, you have to determine. And finally, what I want to say now is that something about the construction. How do you construct such a spacetime? So the spacetime is constructed as a limit of what we call GCM admissible spacetime. So again, you see the same word GCM appearing. So I want to, again, unfortunately, since I cannot point it out, it's going to be difficult to show you various things on the picture. On the upper right-hand side, so you see the picture represented by these boundaries, B1, B bar 1, A at the top, sigma top, and sigma star. So this represents a spacetime which is finite, right? It's a compact spacetime. Obviously, it's a spacetime that you are constructing by a bootstrap argument. You are constructing a sequence of such spacetime which converge finally to the spacetime that you want, which will be the perturbation of Kerr that you have in mind. The most important part of the picture is S star, which is at the boundary on the right-hand side, on the top of the right-hand side, you see an S star, sigma star. So S star is a surface. It represents a two-dimensional surface which has very, very important properties which are called the GCM properties. So S star is a GCM surface. Sigma star, which is the full boundary on the right-hand side, so it's a future boundary of this compact spacetime, is also called the GCM hypersurface, and is actually constructed by concatenations of what we call GCM surfaces. So I'll say, obviously, in a moment, what the GCM hypersurfaces is. So anyway, without further ado, since I cannot really spend too much time on a picture where I cannot point out, the important thing to remember from here is S star and sigma star. The next important thing is that there is a bootstrap argument. So what is a bootstrap? The bootstrap represents a system of bounds for all the important quantities which are part of the proof, right? So in particular, you have a frame, E3, E4, you have the Ricci coefficients, you have the curvature coefficients, and you want all of this. If you subtract from them the Kerr part, you want all these things to be small, but small in a very quantified measure. In particular, you want to control decay, how they decay as you move to infinity. So all those things will be part of what you call the bootstrap argument. So think of the bootstrap argument as being a bound on many, many quantities, bound by some parameter which we call epsilon. On the other hand, the initial data, you have to think in this picture, there is an initial data, which again, I'm not, unless you have questions, I'm not going to spend too much time, since I cannot show it. But the initial, you have to think about the initial data as being small, a small perturbation of the original Kerr solution by a parameter epsilon 0, which is much smaller than epsilon. So epsilon is the bootstrap parameter, epsilon 0 is the initial data. So in the bootstrap means that in the spacetime, which is represented, this finite spacetime, which is represented by the boundary, the bootstrap is estimated by this parameter epsilon. Initial data is estimated by parameter epsilon 0. And you assume that you go as far as you can with a bootstrap. And therefore, you are at a time when all the estimates now are exactly epsilon or are comparable to epsilon. And in order to be able to go further, I have to prove estimates. So this is a physical continuity argument. You have to show that, in fact, the quantities which are by bootstrap bounded by epsilon, in fact, they are bounded by epsilon 0, by a constant times epsilon 0, epsilon 0 being the initial data. So how do you do that? So this is obviously the hard part of the whole thing. So to do it, you need to prove estimate. So there are two types of estimates. There are estimates for the curvature, which are the Tsiolkovsky variables, which are somehow, as I said, somewhat less dependent on the particular gauge. And then there are all the other ones which depend on the gauge. Now, typically, you want to start from the initial data. The initial data here is represented by the lower hand side. So N and 0, you can think about the regions of the spectrum where you control the initial data completely. And now, the way usually one does is that you start from the initial data and you move up, let's say, to a trace star, right? But when you move up, you integrate against the curvature. That's very bad in terms of reading detail. You can do a lot of detail. So instead, what is done here, is that you're actually starting with the star where it's not tied to the initial data at all. You pick up the star in such a way that certain quantities are actually completely controlled. That is where you pick up quantities which are the value but anyway, you have quantities are controlled. Then once I control the quantities A and A bar, which are just Tsiolkovsky bars, which I was saying by hypothesis, which depend on the initial data. Whenever you solve a way, the question falls from the initial data. So you can imagine that the first thing that you do is to show the bootstrap to show that the quantities A and A bar are not measured by epsilon, but by epsilon 0, right? So then using that information and the information that you have on the start, when I make assumptions on the start, I integrate instead of integrating from the initial data, I integrate exactly the opposite way. So, and that allows you to control all the quantities of sigma star, right? So you control all the important quantities in the bootstrap. But now that they are less than epsilon 0, right? Because we are starting from infinity, we already have information. Therefore, you get all the quantities are less than epsilon 0 sigma star. And then when it's from sigma star, you go inside, you transport the operation, again, it's in the story, but then at the end of the day, you show the everything is 0. And the bootstrap is verified. Now, if, the bootstrap is beaten, I mean, you do much better. And that means that you can continue the solution, right? So the solution can be continued by a simple local existence theorem, for example. But then, as I continue the solution, it's not at all clear that I obtain a similar boundary on a star and sigma star. So I have to continue the solution, and I have to construct a sphere, and that's where the construction of the sphere takes place. I have to construct a sphere, a new sphere, a star prime, let's say, which verifies the condition that I mentioned earlier, the GCM condition. And that's, and then from it, I construct a new sigma star. And therefore, I show that a new spacetime, which is larger than the original one, has been constructed, where the bootstrap assumptions are still verified, and therefore I can go forever. Right? So that's the idea. So where the GCM, and that's the only thing I'm going to talk about now, where the GCM, the construction of GCM takes place is exactly in this continuity argument. You continue, you have to construct a new S star and a new sigma star. Okay? And that's these are sort of non-trivial things. So let's go to that now. How much time do I have? Sorry? 10 minutes, okay, good. So finish. Okay, so this is a structure of the proof I already mentioned a little bit. You have equations, E gamma plus gamma times gamma equal R, dr plus gamma times R equal to 0, right? So these are these nonlinear equations that you have to solve. First of all, you control capital A bar, so these are the Tsiolkovsky variable. That's where you use hyperbolic theory. So this is part of the second paper, the big paper that I have with Elena Georgi and Jeremy Saftel. So the whole paper is dedicated to hyperbolic estimate. So it's a highly non-trivial part. But once you have that, then you can go to 4 directly, and you control the curvature, the Ricci coefficients, and the metric on sigma star. Okay? So that's where you use the GCM condition. So the GCM condition plays a fundamental role on this part. And so first of all, you construct a star as a GCM sphere. Then you construct sigma star as a concatenation of GCM spheres. And then you define suitable M and A. By the way, I should mention maybe in the previous slide. You see there is an A and M and an axis. So you define at every stage in this continuation argument, in continuity argument, you construct an A and an M, right? But later on, when the spacetime is being continued, this A and M will be redefined, right? So that's how you solve the problem of not knowing from the beginning what A and M are, because you are constantly redefining the values of A and M. Right? So say you this again, this A and M are defined based on a star and then some kind of continuity construction from AM. You extend the definition to a sigma star, and from sigma star you extend it in the interior of the spacetime. So 4 is whatever happens on sigma star, where again you start from infinity, so you are moving not from the initial data, but from the star, where you have some information from the construction of GCM. And then you go to 3, and you control, once you have the control of all the quantity of sigma star. By control, I mean they are bounded now by epsilon 0, by a constant times epsilon 0, right? Which is from the initial data. Once I do that, I show that by some kind of transport type equations. Again, the structure of the equations is very important. The Einstein equations are really amazing. I mean, they have this absolutely incredible structure without which we'll never be able to do anything. There is some kind of triangular structure that allows you to go step by step and sort of extend the estimate that you have now on sigma star, you extend the criteria, and so on and so forth. It's not, I don't want to go into the details, but the important thing, again, is that the GCM surfaces play absolutely a fundamental role. Okay? Now, let's go to the main ideas, just to repeat what I already said. So the construction of GCM spheres is very important. So these are codimension 2 spheres. What's new here is that there are codimension 2 spheres. Think of codimension 2 sphere. Think of the fact that in geometry, for example, people construct mean curvature foliations on a 3-dimensional surface. You construct a codimension 1 mean curvature foliation, right? And where you prescribe just one condition, which is the mean curvature. Mean curvature is prescribed. Here you have to construct instead 3. You have to prescribe instead 3 conditions. Codimension 2. Obviously, geometrically, it's much more complicated. And this is the first time, in our proof, is the first time that this sort of things show up. And again, since I don't have too much time, I should say it already. I do believe that the GCM construction, in other words, construction of these codimension 2 objects, in which certain specific things are verified, verify certain specific conditions, are going to be very important in all sorts of things, both in geometry and in general relativity, and maybe even in fluid. But in any case, this is the construction of the GCM sphere. Choice of the last slide, so this is the GCM hypersurface, which is a concatenation, in fact, of GCM surfaces. Once you have the notion of GCM surface, you can concatenate and you get the GCM hypersurface. The non-integrability plays a fundamental role, again, because, for example, in the integrable case, the geometry of the horizontal structure leads naturally to elliptic theory, elliptic equations, which are verified. Here you don't have, this ellipticity is completely lost because of lack of integrability. So you have to have new analytic tools to deal with this, but I'm not going to get into any details. Control of the Teokovsky variables, again, is another very important thing, is we are using the Carter operator based on work of Lars and Blue, Anderson Blue, which they were the first to study the wave equation, the scalar wave equation on Kerr, using the second order Carter operator, which I already mentioned. And we have to do something very similar in this much more complicated situation, but the idea is really borrowed from their idea. Okay, so I'll finish with this one very fast. I'll try to say a few words about how do you construct these GCM spheres. So there are two papers which have appeared in 2019. The first paper is you construct a codimension 2 choice of a preferred sphere at infinity. And the second one, you make the construction which is done in the first paper, you make it canonical. So somehow in the first paper, as we shall see in a second, the first paper is you construct a notion of GCM surfaces, but which is not canonical. In the second paper, we show how to make it a canonical thing. And then finally, there are these hypersurfaces constructions based on concatenation of GCM spheres. And this is done in our work on stability of Schwarzschild already. In fact, all these notions already appear in stability of Schwarzschild in our 2018 paper. And then there is a new work of Shen, a student of Jeremy, where he extends this construction that we had in our Schwarzschild paper, extends it to stability of Kerr. Okay, so this. Okay, so there are two modulation. Modulation is a choice of gauge, right? So whenever I say modulation in nonlinear theory, it means finding a gauge choice which allows you to solve the problem. Now, the problem typically does not depend on the gauge. I mean, the final result does not depend on the gauge, but the construction is gauge dependent, right? So the proof requires this construction, which depends on the choice of gauge. Okay, so here's how you construct GCM surfaces. So and then maybe I'll finish with this slide because obviously I don't have much time. So you see, when you do this extension, which maybe I'll go back and show you the extension. Right, so if you look at the picture, as I said, the bootstrap argument allows you to prove, and various constructions that you have, the Teokovsky equation and the GCM, allows you to get a better estimate than the bootstrap argument. Then you extend the solution, and then in that extension, you have to construct a new S star and a new sigma star. So you can assume in the construction of these GCM surfaces, you can assume that you already have control on the portion of the spacetime that has been extended. So you have a lot of estimates. right? And in that space-time, which you control, you have to construct a new GCM sphere, and then later on a GCM hypersphere. But let's concentrate on the okay, so here it is. So you assume that you have a space-time already with an appropriate control of all the quantities. Gamma check means gamma minus gamma of care, and R check means R minus R of care. So you assume that you have complete control on the quantities, and now you want to construct a new sphere, a new four-dimensional sphere. And the way you construct is by fixing. So you want to find a sphere in this space-time on which we have a lot of control. You want to construct a new sphere which fixes the value of trace chi bar. This we have already mentioned, and another quantity. So there are three quantities. So this quantity is expressed in terms of divergence of theta minus rho. Rho is part of the curvature. Anyway, you have to fix three quantities. So unlike, for example, in codimension one, and when you fix one quantity, like mean curvature, you have to fix three quantities, and one more. That there are various conditions which ensure integrability. Anyway, the freedom to choose these three quantities is intimately tied to the gauge covariance of the Einstein equation. So you are using the gauge covariance of the Einstein equations to construct these three quantities, right? To make these three quantities to trivialize. You cannot quite do it, unfortunately. I mean, these are changes. Do I have 2 more minutes, or maybe I should stop? Yeah. Okay. Yeah. Okay. So we have to fix these quantities, and how do you fix these quantities? Obviously, you use the freedom, the gauge freedom. In other words, what you do is that you start up with a frame which you already have, in which you have this control that I mentioned earlier, that I have a lot of control relative to a specific frame. And now I want to construct a new frame, okay, and a new sphere together with this new frame, such that these conditions are verified. I mean, this requires these gauge transformations. So there are these gauge transformations that go from the frame E1, E2, E3, and E4 to E1 prime, E2 prime, E3 prime, and E4 prime. As I mentioned earlier, you can see how the curvatures and the Ricci coefficient change under this change of coordinates. So, so this is how, for example, trace chi bar, these quantities which come in the definition of GCM, this is how they transform relative to these new variables FF bar, which define the transformation. So these are FF bar come up in the definition of condition. Here. So you see in the definition, in the change of frame formulas, there are these F and F bar which show up, and those are arbitrary functions, right? I mean, for any F and F bar, I find the transformation of this. So here is an elliptic system that is formed. But you can see when you identify this, what you want to have is to specify. Again, unfortunately, that I cannot show. I have to specify on the left-hand side, these trace chi prime, and mu prime are exactly the ones which I want to fix. So I have specific values for them, and therefore F and F bar verify certain equations, which are elliptic equations, and there is a kernel. This leads to sort of a definition. Anyway, maybe I should stop here. I think it makes no sense. There are too many more details to be said. But the important thing we should leave from the lecture is that somehow you can use the whole freedom, the whole gauge dependence, the whole gauge covariance of the Einstein equations in order to construct objects which are highly non-trivial objects because they are codimension 2, in which you can specify certain quantities, and the specifications allows you later on to really get a lot of information about the dynamics. And I believe that also potentially useful for other things.
Okay, thank you very much. Let's thank Sergio for this nice talk. Questions?
Yes, so what is the exact definition of GCM spheres? You mean the exact...
The GCM sphere?
Yeah, here, right?
Yeah, so you see, I want to... Unfortunately, I cannot point out to anything. So you see, you want to have a sphere together with a frame, a new frame. Right? So you start with a frame because you have a space-time in which a frame is given and in which a lot of information are available to you. You construct a new frame in which you fix the trace chi prime, trace chi bar prime, and mu to be exactly the ones of care, right? For a given A and M. A and M is also something that you control because you are going to define it. So in other words, you fix three quantities, right? Now it turns out that you cannot quite do it. There are certain problems with the kernel of the elliptic system that you get by doing that is highly non-trivial. So you have to modify the construction by allowing for so-called L equal 1 modes, which correspond to the sphere. They are nothing but L equal 1 spherical harmonics. So there is a concept, general concept that you have to do for perturbation. Anyway, so this is what it is. You have to have three conditions. You cannot quite have it, right? And that's why you have to define this L equal 1 mode. That in order to define the equal modes, you have to do this effective inequality. So anyway, there's a lot of stuff going on. But more or less, you want to fix up certain conditions so that those conditions will help you then to get decay and to get convergence.
Okay. Take one more question. Well, so let me ask Sergio. So this is a very, very major progress on the black hole stability problem, but the full the stability problem for the full sub-extreme range remains open. So could you comment on what in your view, what are the main obstacles?
Well, so for example, this GCM construction has nothing to do with the smallness.
That's right. Yeah.
So this is very general. So the construction here is very general. So in other words, important parts of the proof do not depend on the smallness of A. Right? So where the smallness of A comes up most dramatically is in the treatment of the Teokovsky equation. Teokovsky and generalized Regge-Guder equation. So more or less, if you can deal with the Teokovsky equation in care, using methods like, for example, this kind of Carter, the vector field method, and the extension of the vector field method using the Carter operator, if you can do that in care for
large A,
for large A, I think you will be able to do it. So it's really, somehow the problem is now you can reduce it to something very specific. You don't have to, you don't have to worry about changing the entire construction. Most of the construction stays the same. It's just that you have to be much more careful with
So the overall structure of the proof will remain essentially the same.
The structure of the proof is, I think, exactly the same. You have to be very, very careful on the hyperbolic estimates for the Teokovsky. And there are some other parts in the end, we have to read all. Anyway, there are a few parts, but they're all hyperbolic essentially.
Okay, very good. So let's thank Sergio again then.
Thank you.
Okay, so we're running a little bit late. So the next, yes, yes, exactly. Yes, I know. 5 minutes. Okay. Okay. Right. Yeah. Well, so they didn't think of that. I don't know. Anyway, it's even more people. I think they somehow they all were here like the first couple of days, right?
Hello, can you hear me? Hello?
文教授的那个论推出来。
Hello？
这一场是那个线上演讲，马上开始了，请大家坐好。控台把文教授的 Zoom 推出来。
Okay. I was
请问能听见我说话吗？
Okay, so I think Okay, I think we're ready for the next talk. So our second speaker for this morning is Professor Xiaogong Wen, and I think you're actually in Hong Kong at the moment. Is that
Yes,
correct?
I'm in Hong Kong.
Okay, so let's make sure that we can hear you.
Hello, can you hear me?
No, we can hear you.
Okay, yeah, thank you.
So Professor Wen was a student of Ed Witten, and he got his PhD in 1987 working on superstring theory, and but after that switched to working on condensed matter theory, and has done many important works and has many honors. So he's a member of the National Academy of Science in the USA, and he has recently got a Dirac Medal from ICTP. He was the Isaac Newton Chair at the Perimeter Institute, and is currently a professor at MIT, including other places. So please, Professor Wen.
Thank you very much. Yeah, it's really my great pleasure to have an opportunity to speak here about our work. I really appreciate the effort of the organization committee. Since I'm really sorry I couldn't present my work online in person because I recently got COVID. And I'm really grateful for the organization committee allow me to give this online version. And what I'm going to talk about today is about a new understanding of symmetry. You know, our work started around 2014, 2015. At that time, we are studying the relation between gravitational anomaly and the topological order with Kong Liang and Zheng Hao. And at that time, we realized that topological order actually are described by so-called braided diffusion hierarchy category. So gravitational anomaly and the braided diffusion category have a very close relation. And since 2019, we start to realize that the gravitational anomaly and the symmetry actually is the same thing. So actually, our understanding of a gravitational anomaly can be viewed as an understanding of a symmetry. So the symmetry and the braided diffusion category have very close relation. And this is a story I'm going to tell today. You know, the physics and the mathematics have very close relation. In fact, every major revolution of physics always accompanied by introducing new mathematics. That's a sign of a really fundamental revolution of physics. For example, in the mechanical revolution of Newton, we got a worldview that everything is formed by particle. And then we also encounter a challenge or new phenomena, that is the curved motion of a particle. And at that time, we have to invent new mathematics called the calculus to describe this curved motion, to allow us to even write down the equation motion for the particle. And that's led to this mechanical theory of our world. And this theory, you know, for a long time was regarded as a final theory that explains everything. Currently, we are actually experiencing a second quantum revolution. And in this case, our worldview is very different. At least some of us think everything comes from quantum information, that is the qubits. even our vacuum, our space coming from quantum information. Actually, we can view our vacuum as an ocean of qubits. And all the elementary particle and the interaction can be viewed as a motion of qubits that form of a vacuum. And here we really encounter a new phenomenon. That is a pattern for quantum entanglement among those many, many qubits that form our space. So facing this new phenomenon, and we really need the new mathematics. It turns out that in this case, the new mathematics is a braid diffusion hierarchy category, which happen to be a mathematical theory, at least we believe, describing quantum entanglement of many, many qubits. And from condensed matter point of view, the entangled qubits actually form of many different kinds of quantum matter. So therefore, the braid diffusion category can be viewed as some kind of mathematical framework for those highly entangled quantum matter. And from elementary particle physics point of view, we believe that the vacuum actually is one of a highly entangled quantum matter. So therefore, to study the phenomena happen on top of vacuum, like elementary particle, elementary force, and the braid diffusion hierarchy category also play a very important role. And so today, what I'm going to discuss is a small part of this story. It's about even symmetry in our quantum world, also described by braid diffusion hierarchy category. So we know that the symmetry is defined as invariants, which are described by group. Like we have a pattern, and the transformation that leave those pattern invariant from a group, and that describes symmetry. Here, I want to stress that this definition refers to so-called classical symmetry. The quantum symmetry actually is some invariance of a quantum system, some property of a quantum system, and which in general are beyond the group or even beyond the higher group. So our world actually is a quantum world. So naturally, the symmetry in our world should be described by something beyond the group. So what is this thing? But first, let me explain what is a quantum system. You know, quantum system mathematically is just a pair of vector space and the operator which act on the vector space. Okay, this operator is called the Hamiltonian. A state is a vector in this vector space. A time evolution of this vector or this states is determined by this Hamiltonian in terms of this time evolution operator. Okay, and but we have to define a symmetry a quantum system more carefully. Actually, to define the structure of vector space, we need to first introduce a graph. And so we have this graph. And the vertex are labeled by this I, J, K, etc. And on each vertices, we have a small finite dimensional vector space. And the total vector space, or called the total Hilbert space, is actually tensor product of those small vector space. So therefore, this vector space have structures, have this tensor product decomposition according to this graph. Okay. And this point of view allows us to introduce localness. So we have so-called local operator. Those are operators which act on a single small vector space on one vertex, or several small vector space on nearby vertex. Okay, those are local operators. And then we have algebra of local operators. Okay, and this is play a central role here. The Hamiltonian basically is a particular sum of those local operators, which satisfy this Hermitian condition. So in some sense, what I'm describing here is a mathematical model for all quantum material in physics. So all the quantum material are believed to describe this kind of mathematical model. Here, I want to make a remark that after introducing the graph, we have a sense of dimension. The dimension of the graph is actually dimension of the space, okay, and which is denoted as ND. And sometimes we also use this n plus 1 capital D which to indicate the dimension of a space-time. So they have because time, there's one more dimension. The space dimension is n small lower d. So that's a convention I'm going to use in this talk. So the total Hilbert space. So let's define a symmetry. To define symmetry, let's consider a very special case. That the vector space on every vertex is just two-dimensional. The basis is up and down. You call the spin up, spin down. They form a basis of this two-dimensional vector space on this vertex. Okay. And then we have a so-called Z2 global symmetry, which is generated by the transformation, which is a product of this X operator. This X operator acts on every vertex, just a flip spin from up to down, from down to up. It's a spin flip operator. The product of the spin flip operator on every vertex generates this Z2 symmetry. Then we can define the symmetry, just follow the classical symmetry idea as invariance. So if a Hamiltonian is a H operator is invariant under this symmetry transformation, then we say, yeah, our system have a symmetry. However, this is a wrong way to define symmetry. This way is not really wrong, but too limited. There's a more general or better way to define symmetry. So in this case, we concentrate on this algebra of local operator. Remember, the algebra local operator play key role in definition of quantum system. In the presence of symmetry, we just replace this algebra local operator with the algebra of a local symmetric operator. So that's why we require the local operator are invariant under those symmetry transformation. And then the Hamiltonian is a sum of this symmetric local operator. Okay. So from here, we see that the symmetry is actually not defined by invariance, but defined by this algebra of a so-called local symmetric operator. Okay. And here we can do a generalization. We can pick an algebra of any local symmetric operator, some subset. We have some subset of local operator which form algebra, then we call that symmetry. And the Hamiltonian is the sum of local operator in the subset. Okay. So this is a way to define more general symmetry. Then what do we mean by no symmetry? If our local operator includes all the local operators, then that is the case with no symmetry. If our local operator only includes some subset of a local operator, then that's the case we have a symmetry. So in this case, we define a more general symmetry. And we will see that for this more general definition of symmetry, it is beyond the group. Certainly, this algebra for a local operator have too much information. We need to define the equivalence class of that. That equivalent class correspond to symmetry. Okay. So here I try to define equivalent class. One natural way to define equivalent class is to introduce a unitary operator U. If two algebra of local operator and which are related by this conjugation of this unitary operator U, then we say these two algebra are equivalent. So this is a very natural definition up to this unitary transformation. And here I want to point out that because the algebra, the operator which form algebra are local, so therefore this unitary operator map the local operator in the algebra to the local operator in another algebra. But however, it may not map the local operator outside of the algebra to the local operator to a local operator. So therefore, it's only preserve localness for the operator within the algebra, may not preserve localness for the operator beyond outside of the algebra. Okay. So therefore, we call this a potentially non-local unitary transformation. Okay. And so also the two operator algebra also regard the equivalent if they differ by some operator algebra which with no symmetry. More in particular, suppose we have another two operator algebra, this A and A tilde. which represent no symmetry. Basically, they include all the operator in some other system. And then the tensor product of the operator algebra with the symmetry with operator algebra without symmetry will not change symmetry by definition. So we don't have an additional symmetry. So therefore we have this additional equivalence. It's kind of like a stabilization for fiber bundle. We can add a trivial bundle without changing the class of a fiber bundle. Okay, so using this 1 and 2, we hope we can define a notion so-called hollow equivalence. There's a name, we add hollow. This hollow really refers to this operator U, which may not be locality preserving. If you require U to preserve locality of all local operators, then the U will have a smaller choice. Then the equivalent class will be smaller. For this smaller equivalent class, we will define so-called equivalence relation, not hollow equivalence. Okay. And I want to mention that in physics, most people define symmetry, equivalent symmetry using the second definition as an equivalent. And here we have a more general equivalence relation. We're using hollow equivalence for convenience. Okay. So in the following, we will try to describe what is a hollow equivalent class of this local operator algebra for the algebra of this local symmetric operator. Okay. So let's just again using a very simple example. Again, using the example that on each vertex, we have a two-dimensional vector space, a spin up, spin down. And we also consider one-dimensional system. Okay, so our vertex form a line. Okay. And the Z2 symmetry, again, is just a product of those X operator, which flip spin up to down. Okay. And so we want to find some invariance of this algebra of local symmetric operator. For a particular case, the algebra generated by this X operator on each side, and also on the Zi plus 1 operator on each on neighboring side. This Z operator is operator where spin up is eigenstate of Z operator with eigenvalue 1, and the spin down is the eigenstate of Z operator with eigenvalue -1. So it's another operator acting on this two-dimensional vector space. Okay. So for this kind of symmetry, Z2 symmetry, actually all the local symmetric operators are generated by this pair, these two kind of local operators. Okay. And from this, we can see some invariance. And with physics called the conservation law. So in one invariance, we can see that we can choose a basis, left spin, right spin basis. So actually, left spin is up plus down, and the left spin is up minus down. So just another basis. Okay, it's a left-right basis, not up and down basis. And we choose all the spin pointing to the right as a reference states. Then we call the spin pointing to the left as some kind of excitation, as a something. Then we realize that under operation of this local symmetric operator, this left spin have a mode 2 conservation. For example, this X operator, this left spin or right spin is the eigenstate of X operator, so the X operator don't change them. And the Z operator would flip left to right, right to left. But however, our local operator only have a 2Z operator. So we can only create a 2 left spin. Or we can moving one left spin to another place. So we can never change the even number or odd number of left spin. This evenness or oddness of a number of left spin. So there's a mode 2 conservation. So this mode 2 conservation of a left pointing spin is one of invariance reflecting this symmetry. It's called the conservation law. And in mathematics, we can describe this conservation law using so-called the fusion 1 category. We view the trivial states, this reference state as a trivial excitation 1, and the left spin as some excitation called the E. And the conservation is that the E and the E fused together can give us a 1. So this kind of fusion rule describe a fusion category. So therefore, the conservation law in physics are described by the fusion one category in mathematics in this case. Actually, we have another conservation law. To see another conservation law, we choose this up and down basis. In the up-down basis, we have this domain wall. So in one part, spin pointing up, in the middle part, spin pointing down, and then spin pointing up again. Then between this, then we have two domain walls. And we can see that this domain wall also have a mode 2 conservation. This kind of local operator, ZIZJ operator, and the XI operator cannot change the evenness or oddness of the domain wall number. Okay, so in this case, we can choose a reference state, this up plus down, which are symmetric under this symmetry transformation as our 1. That's reference state is up plus down. Then this domain wall M as an extension, and this as another object. Then the mode 2 conservation, I described this fusion of M fused with M give us identity, trivial excitation. So there's another fusion one category called VEC Z2, which also describe another conservation of this Z2 symmetry. So the bottom line is that this in one dimension, the Z2 symmetry contain two conservation. Or mathematically, you say contain two fusion one category, rep Z2 and VEC Z2. This describe these two mode 2 conservation. But actually, this 1D Z2 symmetry not only contain these two conservation described by these two fusion one category, it also contain more structures. And also these two fusion one category are not independent. They do not correspond to different Z2 symmetry. They are related. And their relation also encoded these additional structures. Okay. So later we'll show that we can combine these two fusion one category together. Actually, this Z2 symmetry is described by a non-degenerate braided fusion one category, which is also called a modular tensor category. And in this case, for Z2 symmetry, this particular modular tensor category is called a Z2 quantum double, which contain both rep Z2 and VEC Z2, because this modular tensor category have a forgettable functor into a fusion category, and which allow us to obtain the VEC Z2 and rep Z2. Okay. And this turned out to be a very general picture. So we there's a conjecture that in n-dimensional space, every quantum symmetry, the symmetry of quantum system, up to the hollow equivalence, is described by a non-degenerate braid fusion n category. And for the Z2 symmetry, here it's just an example of this more general conjecture. Okay. So how to show this conjecture? And so our starting point is operator algebra of these local operators. Remember, our operator algebra is generated by the X and a pair of Z operators. And we try to claim that within this operator algebra, it's encoded a braid fusion n category, and we can recover braid fusion n category. And that's describe the symmetry of this operator algebra. And although here we emphasize that this operator algebra are algebra of a local operator, the operator act on nearby vertex. Okay, but in order for the algebra to be closed, we would allow many operators to multiply together. We may get very large so-called non-local operators, some kind of like a string operators, which are included in this algebra. So very long string operator, we call the patch operator. And here we want to emphasizing a particular patch operator, which is very useful and which help us to extract this braid fusion n category. And this we call the transparent patch operator. And this transparent patch operator is defined as some kind of patch operator like that, but have subject a condition that is commute with all the local symmetric operator. This local symmetric operator, as long as this local symmetric operator is far away from the boundary of a patch. Okay, if they far away from the boundary, even inside or outside, as long as far away from boundary, then they commute. Okay. So because of this, we call this a transparent patch operator. Okay. The reason we want to introduce transparent patch operator is we try to recover this conservation law. This conservation law is called the super selection sector in physics. And then we hope using transparent patch operator, we can recover the super selection sector, which reflect like conservation law we just discussed before. And here we discuss one-dimensional patch operator, which is just string. In two dimension, the patch operator can be a string-like, open string-like operator, or can be a disk-like operator. Okay, for disk-like operator, the boundary will be a loop. In three dimension, the patch can be open string or disk or a ball in three dimension, etc. Okay, and those patch operators have a lot of equivalence relation. And again, I don't think we have formulated in very general way, and but at least include the following thing. We can multiply a local symmetry operator on the boundary of the patch operator, then this without changing this equivalence class. So the two patch operator who at the boundary differ by a local symmetry operator would regard as equivalent. And also, if two patch operator differ by some kind of unitary operator construct from the local symmetry operator, and they are also regarded as equivalent. Okay. But anyway, here I just want to emphasize that this patch operator have a lot of equivalence relation, and they led to this equivalence class. And this equivalence class of those patch operator will allow us to recover the braid diffusion category. Okay. So the idea is really the following. The patch operator have an invisible bulk. Remember, the bulk of a patch operator commute with all local symmetry operator. And the local symmetry operator, which form algebra of a local symmetry operator, is all the observation, all the physical measurement you can do. Okay. So from that point of view, from local symmetry operator point of view, the patch operator have an invisible bulk, essentially have no bulk. Only the boundary patch operator is visible, is important. Okay. For example, a string like a patch operator should be viewed as a two particle at the string end. A disk like a transparent patch operator, we call the T patch operator, actually is can be viewed as a closed string on the boundary, at the boundary. Okay. And so therefore, this algebra of some T patch operator would give rise to this braid diffusion category. And if algebra for all the T patch operator, then it will give us a non-degenerate braid diffusion category. Okay. So here, for example, in three dimension, the boundary patch operator may be a two-dimensional surface, and that can be viewed as the object of a braid diffusion. I think that's a braid diffusion 3 category. Okay. And then the boundary of this like operator will be like a string-like. Then that can be viewed as a domain wall between membranes, between surfaces. So that's like a one morphism in this braid diffusion 3 category. So therefore, the different dimension of the boundary of the patch operator correspond different level of morphism in the braid diffusion category. So this is how this transparent patch operator and the braid diffusion category are related. And it's really from this relation, we try to show that the algebra of this T patch operator actually encode a non-degenerate braid diffusion N category, which in turn describe a symmetry of the quantum system. And so again, we are going to use this our Z2 symmetry as a simple example. Try to demonstrate, this idea is maybe okay. Remember, for one-dimensional Z2 symmetry, it should correspond to a non-degenerate braid diffusion 1 category. And this particular braid diffusion 1 category turned out to be a Z2 quantum double. which is a modular tensor category, which is Z2 quantum double. In general, a modular tensor category is described by some data, like n. N is the number of objects called a rank. And this object have a fusion ring described by NABC. And then there's an associator called F symbol. And there's a braiding, self-statistics, self-braiding, and mutual braiding. And so those data describe this modular tensor category. So I will try to illustrate in this simple example how we calculate this data from the operator algebra. Okay, and first this so-called transparent patch operator for the Z2 symmetry, we have 4 equivalent types of a T-patch operator. The first one is trivial, just an identity operator, which is a trivial string. Then another one is called the OM string, which is a product of X operator from I to J along a segment. And then we have another string operator, just a Zi times Zj, but nothing between I and J. So is this one have empty bulk? We view this pair of Zi, Zj as a string operator with empty bulk. We call this E string operator, and this X is M string operator. Okay, and then there is a product of a E string operator, M string operator gave us F string operator. So therefore for the Z2 symmetry we have these 4 types. Okay, so therefore this modular tensor category we try to calculate should have a rank 4. Okay, and there's 4 simple objects which is labeled by 1, E, M, and F. Okay, and I remember that this M string operator actually perform a Z2 symmetry transformation on the segment over a patch, not everywhere. Okay, so that corresponds to the patch symmetry operator. Okay, however, this E string operator create a pair of Z2 charge at the string end. This Z operator actually create Z2 charge because this Z operator transform non-trivially under this Z2 symmetry transformation, they change in sign. So therefore, they create a pair of Z2 charge at the string end. Okay, but overall, this E string operator create a 0 total Z2 charge. Just on each end, they create a non-trivial charge. Okay, and so that's why we believe these 2 string operators are inequivalent, because they have this interpretation. Okay, and naturally, this open string operator or T-patch operator has some natural algebra. For example, the square of E string operator equal to 1, square of M string operator also equal to 1, and also we can join 2 string operators together from string ij, and j can join together to form a string operator from I to k, and etc. So those are some kind of algebra of this E string operator. And from this algebra of E string operator, from string operator, we can infer the fusion ring. For example, we can view this like an E string operator as creating 2 E particle. Okay, because it's creating like a 2 E charge, this E particle. And then we interpret the square. Remember, square of E string operator is identity. So that's like a creation operator of 2 E particle at the I side, J side, become, if you square it, become identity. That's from that we infer that the fusion of 2 E particle became trivial, became identity. So therefore, from this kind of operator algebra, we infer the fusion ring for the end of a string. Okay, and so therefore, from this operator algebra, we recover the fusion ring. Okay, so that's the only part of data. And the modular tensor category contain more data than fusion ring. Okay, and the next data we want to extract is called associator. Because when three object fields like A, B, C fuse together, we get a D. But however, A, B, C can fuse in different order, like A, B fuse first, then fuse with C, and B, C fuse first, then fuse with A. Okay, these two different order would produce the same excitation D, but from quantum theory, those excitations are described by wave function, but the wave function differ by a phase factor is viewed as equivalent. So therefore, the different order for fusion although produce same D excitation, but they may differ by some kind of phase factor, some kind of complex phase, or more generally, some unitary operator. And it's called F symbol or called associator in the category theory. So therefore, using our patch operator, we can also compute this associator of the fusion. And remember, the patch operator is just is like a hopping operator for the particles. Those objects E and M can hop around, and this hopping operator are given by this patch operator. And to fuse A, B, C together, we can fuse in this diagram. From up to down, you can view it as a time direction. We first like the B hop from 1 to 2, then A hop from 0 to 1, and then this A and B fuse into some AB at site 1 and etc. You may ask why we kind of hopping around then fuse. The reason is that here we have to choose a gauge convention. That when you fuse A and B together, we always fuse them in the same way. Always fuse some A and B on the next vertex, then fuse them into a single particle, say in the first vertex. Okay. We insist on fusion two particles always in the same way. So we can use the hopping to adjust position of A, B, C, so that when they fuse, they always fuse in the same fashion. Okay. So this is like doing some gauge choice, which is fixing some ambiguity of this F symbol. Okay. So when we do that, and then we find that there's two different ways of fusion. These two different order fusion can be realized by different way to apply this T-patch operator. We apply those T-patch operator in different order, which is realize this different associator. And then the difference between this product, these two operators in different order, would give us this phase factor, which is the F symbol. Okay. So using this, we can compute additional data for this T-patch operator, and which is a F symbol. And after we get F symbol, what we got is a fusion category. Not only fusion ring, now we get the fusion one category. Okay. But to get the braided fusion category, we need additional braiding data. The braiding data is obtained similarly. For example, we want to exchange two A at site 0 and A at site 3. We want to switch their position. We want to make the A from 0 to 3 to 1 and 2. But there are two ways. 0 can go to 1, 3 can go to 2. Or 0 can go to 2, 3 can go to 1. So there are two ways for them to exchange. Okay. And these are two different ways of arrangement, also differ by a phase. Okay. It turns out that this different braiding can be realized by applying this T-patch operator, 3 T-patch operator in different order. Okay. And then if they differ by a phase factor, then that means we have a non-trivial braiding. So therefore, this braiding between two objects in modular tensor category can also be described by this T-patch operator. Okay. And so this basically gave us the idea, how to compute modular tensor category, more generally braided fusion N category from T-patch operator, from this operator algebra construct from local operators. And so from here, we just obtain a modular tensor category. So therefore, this modular tensor category describe a symmetry. Okay. So armed with this understanding, then we actually have a classification of a 1 + 1 dimensional quantum symmetry. Usually we know the symmetry is classed by group. Okay. But actually the quantum symmetry is beyond the group. They are actually classified by so-called modular tensor category. Here I want to say that a modular tensor category here, we considered, we have assumption, we assume they have finite rank. So actually, in this case, if you're using this kind of modular tensor category, they only classify so-called 1D finite symmetry. Okay. Okay. So, but however, I want to say that they classify finite symmetry up to this hollow equivalence. And another remark I want to make is that not every MTC, modular tensor category, describes symmetry. Only a subset of MTC describes symmetry. Okay. And we require MTC to be in the trivial width class. Okay. So that's the more complete classification statement. The 1D symmetry up to hollow equivalence are one-to-one classed by MTC in trivial width class. Okay. So that means they are dream field center of some fusion category. Okay, and recently we classified using computer program, classified the modular tensor category up to rank 11. So those are number of modular tensor category up to rank 11. With some caveat, actually, there's a certain small uncertainty here. Okay, and then among those modular tensor category, a small subset of them belong to trivial width class. For example, at rank 4, we have 18 modular tensor category, but 3 of them belong to trivial width class. So therefore, at rank 4, we have 3 different type of symmetry up to hollow equivalence. And one of 3 is a familiar thing we discussed. It's a Z2 symmetry. The Z2 symmetry have Z2 charge, have Z2 symmetry defect. The Z2 charge, Z2 symmetry defect together, and their bound state from this rank 4, from object in the rank 4 modular tensor category. Okay. And so what the other 2? The second one of the 3 actually is an anomalous Z2 symmetry. The quantum symmetry can be anomalous. They are described by a symmetry together with a cocycle of that symmetry group. Okay. The second one is so-called anomalous symmetry, anomalous Z2 symmetry. And there's a third one. The third one actually is new. The third rank 4 symmetry is a non-invertible symmetry. And I don't know how to describe them except using this fusion category or modular tensor category, So they're truly beyond the group and beyond higher group. So there's so this non-invertible symmetry is the simplest non-invertible symmetry in 1 dimension. It's described by so-called double Fibonacci modular tensor category. Okay, and actually at rank 8, okay, we have 6 different symmetry, but actually all these 6 symmetry correspond to S3 symmetry, and they're anomalous S3 symmetry. Okay. So we don't have a non-invertible symmetry. But at rank 9, we have an additional non-invertible. At rank 10, we have all these 3 non-trivial symmetry are not group-like. They are not even anomalous group-like symmetry. Okay. So this reflects some of our understanding of the symmetry of quantum symmetry in quantum system. And my emphasis is that they are beyond the group. We need to use a modular tensor category or braid fusion higher category to really describing them. However, here I want to say that we only describe symmetry up to hollow equivalence. Remember, we can have a smaller equivalent class. So can we describe symmetry, class symmetry up to equivalence using the smaller equivalence, not up to hollow equivalence? Okay. And so using the remaining 15 minutes, I will quickly describing some progress in this direction. Okay, and here I want to introduce some concept of a quantum state of matter, and what is gapless state and what is gapless states, which is a pretty common concept in physics, but because this is a math conference, I feel maybe I need to introduce a little bit. Remember that the quantum system is described by a pair, vector space and the Hamiltonian operator in vector space. And the lowest eigenvalue eigenvector of the Hamiltonian is called the ground state, or is called the quantum state for this quantum system. So quantum state of a system is just the lowest energy state. So-called lowest energy means the lowest eigenvalue of this Hamiltonian operator. Okay, and the state is gapped if the spectrum of Hamiltonian above ground state have a window, and this window remains finite in the limit of many vertex. We have to take thermodynamic limit, take a limit of many vertex limit, so that this window should remain finite. Okay, then that gives us a gapped state. Okay, and there's too many gapped states. We want to define some equivalence relation. We say two gapped states are equivalent if they can deform into each other by changing Hamiltonian, but without closing the gap. So therefore, there's a family of Hamiltonian which allow us to deform one gap state to another gap state. Then these two gap states would belong to one phase. So that's the notion of a phase of matter in condensed matter physics. Okay, and so there's a bigger story I did not describe, is that actually we have a classification of these gap states, and we believe that this n-dimensional gapless phase, which we call the topology order, this phase of topological quantum field theory. This phase is classified by non-degenerate Bragg diffusion n category. Okay, so therefore this non-degenerate Bragg diffusion n category and the gapped phase have very close relation. So this is what I mean at the beginning of my talk. I say that the pattern of quantum entanglement are actually described by this Bragg diffusion higher category. This will refer to these results. Okay. So this result essentially allows us to have very systematic understanding of all gapped phase of matter. But however, there's also gapless phase of matter. Okay, the gapless phase of matter correspond to the Hamiltonian will have continuous spectrum in the n go to infinite limit. When the number of vertex go to infinity, the spectrum became continuous. Okay, and for the gapped system, it's easy because in physics, we're interested in the low energy property of a system. For gapless system, low energy means they are just a degenerate ground state. It's only ground state matters. So it's very simple. So this result really refers to some very simple results. But for the gapless system, below certain energy scale, we have a lot of spectrum. The low energy physical property is highly non-trivial. And this highly non-trivial low energy property of the gapless state, we believe are described by so-called quantum field theory. Actually, quantum field theory introduced or invented to describe a gapless, a low energy part of gapless states. So there's a notion of a quantum field theory. And understanding gapless state, classified gapless state, and the classified quantum field theory is one of the major challenges in theoretical physics. Okay. And so in this regard, we can also introduce a notion of anomaly-free quantum field theory and anomalous quantum field theory. Okay. A quantum field theory is anomaly-free. It can be realized as a low-energy effective theory of a quantum system in the same dimension. Basically, this kind of spectrum really describes anomaly-free quantum field theory because the spectrum coming from gapless or coming from a quantum system defined on the graph, some defined lattice. If if a lattice quantum system can produce a low energy effective quantum field theory, that low energy effective quantum field theory by definition is normally free. But sometimes quantum field theory can have its own life. Some quantum field theory looks very consistent, very well defined, but somehow we have trouble to find a lattice system or find a graph system to realize this particular quantum field theory. If that's the case, then we say that quantum field theory is anomalous. If there's abstraction to realize this seemingly consistent quantum field theory using a lattice system. Okay. And then there's a conjecture that anomalous quantum field theory can always be realized as a low energy effective theory of a boundary for topological order in one higher dimension. Basically, remember topological order is just a gapped face of matter. So this bulk is gapped, but the boundary can be gapless. And this boundary gapless state can be described by quantum field theory. And if topological order in the bulk is non-trivial, the boundary quantum field theory will be anomalous. Then there will be abstraction to realize this boundary quantum field theory by a graph without going to one higher dimension. So from this point of view, this gravitational anomaly, this anomaly we talk about actually is gravitational anomaly. The gravitational anomaly is classed by topological order in one higher dimension. Remember, topological order are described by braid diffusion n category. So therefore, gravitational anomaly in n-dimension space is classified by non-degenerate braid diffusion n category. Yeah, so basically that's a mathematical statement of these results. Okay, and so using these two concepts, now we can discuss another way to look at the symmetry. But this new, actually more general way to look at the quantum symmetry start with trying to define the morphism between quantum field theory. This is actually a major contribution of Kong Liang and Zheng Hao in this paper. They are thinking about how to define the morphism between quantum field theory. Because quantum field theory is a very important concept in physics. And the morphism is also very, very important concept in mathematics. And so understanding the morphism between quantum field theory probably is also very important. Okay. And so to define this morphism, it's kind of like define some kind of equivalence. So we ignore certain property of quantum field theory and care other properties. And so therefore, this like to introduce it's called hollow equivalence between quantum field theory. This hollow equivalence means low energy equivalence. That means if a quantum field theory, if you start with a gapped system, then we say the low energy property not changed. So therefore, they are equivalent. So more generally, we say that two quantum field theory are equivalent if they are identical after stacking with a gapped system, some gapped TQFT or something like that. Okay. But however, this definition is too naive. So we can generalize definition to anomalous quantum field theory. So we have a quantum field theory, which is a boundary for bulk. So this quantum field theory is anomalous. We have another quantum field theory, which is also anomalous, which is a boundary for bulk. Okay. And then these two quantum field theory are kind of hollow equivalent. If these two quantum field theory, if a first quantum field theory can be viewed as stacking of a second quantum field theory with a bulk M with another gapped boundary. So this M and R. M is a gapped bulk, and R is a gapped boundary. So they that the quantum symmetry are described by fusion N category, which is describing this fusion of a symmetry defect. Okay. So this picture are really recently are just pushed by this paper in 2020 and also by this paper in 2022. And in 1+1 deconformal field theory, this picture also recovered or realized in 1+1 deconformal field theory, many years ago. Okay. So to summarize, is that the essence of symmetry is things should be is a topological order in one higher dimension, or is really the non-degenerate fusion category. And using this new understanding of symmetry, we hope we can have some breakthrough to understand the gapless quantum system. Thank you very much. Yeah.
Okay, thank you very much for this this interesting talk. So, are there questions from the audience?
Sorry, I cannot hear whether someone can repeat or whether can get a microphone.
Consider all topological orders, how one topological order varies to the other, changing to the others. I mean, okay. I mean that if there is a network about the description about the topological orders, each topology is considered as a vertex of a graph, and whether you have a graph connection to describe the all topological types or topological orders you described from the system built up. Yeah, that's the question.
Yeah, sure. And so maybe let's at the beginning. And so remember, a quantum system are defined on the graph. Okay. And then in physics, we need to take a limit where this graph is very, very big, have a lot of vertex. So that's we call the thermodynamic limit. Okay. And for this quantum system on the graph, we have this Hamiltonian. And this Hamiltonian have a spectrum. If this spectrum have energy gap, then we say this quantum system actually have energy gap. It's called a gapless system. If two gapless systems can be continuously deformed into each other without closing gap, and this equivalent class will be called a topological order. Okay. So actually there's a lot of definition at the beginning. But the claim is that this topological order is classified by the Bragg diffusion N category. The reason is the following. You know, when you have a ground state, we believe the property of a ground state are encoded by their excitation. We can create excitation above ground states. And those excitations can be string-like, membrane-like, point-like, and those excitations can fuse, can break. Okay. So those are like a defect in the ground state. It's kind of like the ground state of the quantum system is have nice quantum entanglement. But however, excitation like a defect in the quantum entanglement. And we believe the defect, the property of a defect of a quantum of a defect of entanglement encode the pattern entanglement itself. Okay. So this is because of this. That's why we have this conjecture that the Bragg diffusion N category classify the gap, the quantum phase, because the Bragg diffusion N category is happen to be a natural theory to describe a fusion and the breaking of excitation above ground state. Yeah, I'm sorry, I have to using some physical language to describing this idea. I don't know how to really follow it within mathematics.
It's more of another one. It's higher. The level is it's not about the graph itself. It's about the states. That means the orders. That one formed another kind of connection. That's a category of a category, something like that. All right.
Okay, yeah. So you're totally right. Then you can at an even higher level, and you can view the different ground states as an object of another category, and so you may have a category describe all topological orders together in one piece. Yeah. So that's indeed there should be such a theory in one.
It's very much level. Like how the phase transition, how the one phase changes to another one. You have many phases.
Exactly. You're totally right.
From another network, okay.
That's
a big graph, different graph from the ground state. Yeah.
We totally agree with you. Yeah, and actually using more fundamental language and even view phase transition between different topological order as a morphism, then to build even bigger category. This category would describe phase transition between topological order. That's even more unified theory. Yeah, and even maybe better theory. Yeah, I should use that language. Thank you.
Thank you. Wonderful lecture. Yeah.
Okay, so thank you very much. So I think we're